Awesome. Hello, everybody. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device here for discussion 112. This is Thursday, December 7th, 2023. And this is for advanced PyTorch Keras deep learning with QML/QML algorithms. So this first thing is basically, kind of stumbling upon this for a number of times. I've did these demos, iterated on them twice, and basically seeing kind of what they have to offer is basically there's high dimensional data that you can't do quite effectively with state vector algorithms. So if you get, this is basically the number of nodes, and there's some other options of dealing with that. You could use tensor networks, but in the case with this, it's appearing that you can actually use smaller algorithms that are effective, massively parallelize them to gain this, the quantum mechanical benefits from each of the individual ones. So, this is not for algorithms that are meant to, be larger algorithms, but in fact, maybe 2-qubit, 4-qubit, something like that, or at least these are the ones that I explored. With tensor networks, you can do high dimensions. So these are like matrix product states, and these are, say, for instance, tensor tree networks, TTNs, but they're approximates, right? So it's not an exact like state vector algorithms. So there's some benefit, it looks like, with the parallel processing. Now, if you've ever made your own neural networks, it's a fun thing to do. Once you make your first one, the other ones, in my opinion, are a lot easier. But they have these certain functions, depending if you're using, Keras or PyTorch, concatenation, stacking tensors, and obviously you'll see this sequential, term that they use for containers. And we already can use quantum algorithms with ResNets, BERTs, which is a type of transformer for text. And it's just a matter, and I'll be unveiling basically what's happening here with some of the limitations that we have in using, advanced devices, multi GPUs, with some of these models. Now, in all these things, you have to have a good algorithm. If you go to parallelize all these mini algorithms, it's not going to do you much good. So you really have to find a good embedding. Embedding are usually non-trainable quantum parameters first, okay? Now, the next steps after that, so say, for instance, you're going to have to do some studies. So say, for instance, like, once you have the embedding, try additional trainable layer. And I've done a number of these studies, getting up to, say, like 8 layers was the most effective for both of them. So that's a good number to try. So of course, these are going to add costs, computational costs, but you just can't go wrong having a good embedding and doing a fair number of research with it before you pinpoint the ideal number of layers, say trainable layers for some of these quantum algorithms. Now, Qiskit has torch connector, and the main thing is this neural network is an abstract class for estimator QNN and sampler QNN. So if you're doing either of these, estimator or sampler, these are the ones that you're going to be working with, okay? And, so say, for instance, you can take advantage of PyTorch's automatic differentiation, but there seemed to have been an issue with this specific model. And I was able to pinpoint it as far as, running significantly faster on 3 different collab devices, as opposed to inside of Qiskit lab, where everything should work in theory better. And that was my understanding going into it. But it has to do with how these, in specific, the PyTorch is meshing with the that specific version of other things you have in Qiskit. So for whatever reason, I'll show you, I did benchmarkings at the end with this stuff. Okay, so a lot of these is just business as usual, and what makes it unique is now you have this quantum circuit. So this in specific is the one, my algorithm, that I found worked better than theirs, which is a single ZZ feature map that's embedding. And then a lot of times you have to be careful because this 2 is for the number of qubits. However, the number of repetitions is not shown here. You have to look to documentation. It's usually like 3 or 2 or something like that. So anyways, you have to be aware of using different, embeddings and onsots and Qiskit. And basically, so, this real amplitude set to 1, and it's this QNN. This, you have this quantum effects inside, classical hardware. All these are either CPUs, GPUs, TPUs, or some variations of those. And that's, where you're getting the sum of the whole of using, quantum physics instead of individual bits like you normally would, or how you think of bits in, say, like a convolutional neural network, or say like a transformer. Okay, so now that you have your QNN, you're going to go over, and this should look very familiar. And there's a couple ways in Torch that I've seen, and I would think that this is maybe the most complex one. I had issues as far as, I mean, you can't do too much. I mean, you can add convolutional layers. Dropout, I could change that, but didn't have much luck. So dropping out, weights is effective for minimizing overfitting. It's set to 50% or P equals 0.5. I change it to 0.48 all the way down to 0.4. And then on the other side to 0.6. And actually the best results were just how it is. Like, that's where you have to be careful. You have to understand that a lot of these you can change. And so anyways, you're basically set up with this self.qnn equals torch layer, and this QNN is your circuit over here. Now, if you want to set these up, and like I said, tried ad nauseum. Like I said, this one takes a little bit because it seemed like in different parts of the notebook, as far as setting up inputs, outputs, it was a little less user-friendly than, say, like the Pennylane was. And anyways, if you want to do like a self.qnn1 or self.qnn2, it would still be equal to this torch connector QNN, unless you wanted to use some other quantum algorithm. Okay, so a lot of this is very familiar to people that do neural nets, and you see with the forward pass, both of these should be set up correctly. I have gotten good results by just setting up this in a different model, but in general, it's this x is equal to self.qnn in between two fully connected layers there. So this sets things up, and like I said, with these previous two iterations, I didn't get quite as much into the neural network, but just tried to find ways to, improve accuracy, changing the learning rate to, it was actually a little bit low. So I increased it, which, anyways, that's not always the case. Usually you have to decrease learning rate to improve results, but not in this case. And then also on the second iteration, I introduced weight decay. So weight decay is basically, it limits the strength of the weights. So instead of them getting so high, which takes more compute, and then also, this is associated with better results. So having that learning rate of 0.003, and then the weight decay of 0.01 in the second iteration. Now, like I said, I tried ad nauseum to really get the Qiskit to work, and I believe the neural network was intact, and I had some assistance with OpenAI with it. But like I said, there were some other issues with the rest of the notebook, and anyways, I'll try again. But with the Pennylane one in specific, so this one is the PyTorch, and the PyTorch tutorial and the TensorFlow, or sorry, the Keras, are very similar, so a lot of these, you have a Q node, and it's effectively treating it as the term that they use. There's some rules you have to follow, like inputs and weights. So inputs are going to be non-trainable parameters, and then trainable weights are going to be the more machine learning part of the QML, where they get updated over the course of time. But it behaves, once you have the circuit and it's in the specific format, you can put it in. So your Q layer is effectively this QML.qnn.torch layer. And this takes the Q node, which has the quantum circuit and any weight shapes. And weight shapes is a function of the embedding and the trainable layers, the inputs from the embedding, and then the trainable layers actually, I'm sorry, weight shapes is a function of layers, which is going deeper, and then qubits is what you'll find there. And then, so this is basically the code that I did a lot with. Now, anytime you see it, algorithms, first run it and see what you get. And I think the stock, solution for this was about 86%. And this used an embedding layer and some form of onsat. So my guess is they didn't really take time to test, say, for instance, like 10 layers to determine which of these basic entangler layers is the best one, but it's set to 6 here. So you look up in Penny Lane's documentation, and it'll essentially tell you what the circuit is. And sometimes it's tricky to visualize or draw these circuits. If you want to do something, it's QML.draw underscore matplotlib. Those tend to be a little less compatible, like universally compatible with all different types of onsets. So the stock model is basically this, is you have this 4 neuron classical layer, which is represented by this 4 up here. So when it says torch.nn.linear 2,4, this 4 is that classical layer with 4 nodes. And then the next ones are basically all based on this, original circuit. So these 2 green ones are the, you're going to have your angle embedding, which is set to X. So it's going to be Rx, it's 2 qubits, so Rx, Rx. And then the next one is basic entangling layers and entangler layers. So this is going to be 6 layers of this specific thing. So basically, the important one with this is you need to change the 4s, okay? So the 2s stay the same because the 2 output is classifying binary data set. So if you have 2 circuits that are 2 qubits, that's 2 times 2 is 4. So that's why this is 4. And you see, so 4 nodes and 4 total qubits, for both circuits. So, and I'll show you some bigger examples of this. And then basically the forward pass, and again, this one just made more sense, and this is also written in Torch, but like I said, the way the first one was written with Qiskit, it was more challenging. But basically, to make things parallel is you have to split the 2 layers. So torch.split splits them, and then it says down here in the forward pass what X1 and X2 actually are. And then the concatenation is when it comes back together, okay? And then you're going to a C layer with 2 nodes here, okay? So in everything I ran, the output of the classical layer is 2, okay? But the input of how many classical neurons I want to use has to match the number of total qubits from all the circuits. And I hope that makes sense. Okay, so here was another one with additional iterations. So as you can see, with this first specific one, this was actually incorrect. So I didn't change the forward method, right? So I just added the layers, but not shown in the code, and that's probably reflective of that result. And then this one actually the same thing too, but I changed the algorithm to a very effective. So it's 2 qubits. So it's going to go, and I set the rotation RY. So it's 2 RYs vertical, and then another set, and then the 4th set for this specific one. And it got 99.5%. And the interesting thing is, I said, like on this specific one, I didn't know how to do the forward method, and then I fixed it. I got the same accuracy, but the loss was lower, and it took longer because it was properly set up. So you can't always rely on accuracy. And I'll give you some cases up here. So to get a better visualization of this is if you want to run, 4 of these 2 qubit circuits, you're going to need 8 neurons for your classical layer. Okay. And again, this is the algorithm that I found. If it was 2 qubits or 4 qubits, this one worked the best. So when I came around and basically fixed the, forward method, I got this, lower loss, so 0.028, 99.5%. And with a 400 data set, it actually is better at accuracy. So when you're dealing with data sets, you really have to think about what they are. And in this specific case, I believe this orange dot that's very close to the blue ones That's why a lot of these were stuck at 99.5%, or it's 199 divided by 200. And if you look at the 400 data set, it's more favorable to be classified. So it was easier to get that 99.75%. And when you can visualize your data sets, it always helps. Okay, so switching to 6 of these Q layers, so this would be, 6 times 2. So my classical layer neuron is going to be 12 in this case. And then, going, more and more with this with the 200 data set, and then getting to the 32 Q layers with the 200 data set, there's basically, I haven't got that 100% yet, but with the 400 data set, which is effectively easier, I was able to get this 100%, okay? Because, like I said, I think it's this one orange dot that makes it more challenging to classify. And I went all the way up to 64 parallel 2-qubit circuits. So 64 times 2 requires 128 neurons. And then, so the loss decreased over every single run. And the accuracy, I never got to 100%. However, with the 400 data set, with either 32 or 64 layers, I got to 100% of this right data set was correct. And the synopsis is more 2-qubit parallel circuits decrease the loss and improved accuracy, especially for the 400 data set. Okay, so this next one is an example of a couple iterations. And like I said, with this specific one, sometimes you'll actually get you'll get correct accuracy or better accuracy, if you forgot to fix the forward pass. So anyways, on this specific one, it was just fractionally better through these iterations for Keras. Now the Keras one is very similar to the PyTorch one, and I wanted to try something new and different. So basically what I did for this is that, this is the more stock solution on the left. So for the algorithm shown, which is slightly modified from the original, the authors, and then you have the other, 4IRY, which is the working algorithm. And you see it starts at 98% for that and 86. And in this case, instead of going more parallel, I just went in more series, right? So this is effectively 2 identical 4-qubits. So the first circuit is here, okay? And then the second circuit is here. So that's the parallelization. And then from there, I took that and then just took it in series, right? So like it's not parallel, it's in a row. And then you could just see the loss go up and the accuracies go down. And what's interesting is for this algorithm that was less performing, it declined least than the better performing algorithm, because things just weren't set up right to be, or that algorithm wasn't like the top algorithm. So that happened, and basically this went all the way to, I call it a 2-2-2, or effectively, two algorithms, another 2 algorithms in series, another 2 algorithms in series. Each of those sets are in parallel. Okay, so more circuits in series reduce performance for both data sets, and you can see for the best algorithm from 98% all the way down to 50%. And these were for the 200 data set. So I tried 2 different sets of algorithms. So this is not relying as much on parallelization, and it's more on series. And basically this one's not working as well. Now these next 2, basically the left one is a 4-qubit version of the author's algorithm. So this is just, an algorithm that basically didn't really surpass 86%. And that was the same case here. But when I switched it for the modified algorithm that I use, and, basically doing 8 times 4, so that'll get you 32 neurons for the classical layer, this is the best algorithm. So I had a harder time with the PyTorch model getting to 4 qubits. But for this specific one on the harder data set, this is the only one that got 100%, which would, in theory, include this one orange dot there that was harder than, if I double the data. So in summary, so 8 4-qubit circuits in parallel was effective to achieve 100% on the harder 200 data set versus 64 by 2. So if you were to count just pure qubits, 32 qubits work better in this specific configuration than 128. And so you can't, like, these things are like, again, they're smaller algorithms, so you're not going to be able to do certain things, with bigger ones. But the hope is try to get this, especially quantum interference, and you can have entanglement and superpositioning too, but capture the quantum benefit without suffering with the time and the RAM requirements of very, very wide state algorithms, or many qubit state algorithms. So what I did for this, and I added to the number 1, so variational quantum algorithms, I added to this is basically higher dimensions with smaller circuits in parallel. So it'll be interesting to see, what people, and these demos aren't brand new, but what people can get running smaller circuits in parallel. In the main thought is either new utility, but it's basically, the results seem to show that there's some type of additive quantum effect by running them in parallel without using nearly as much time or RAM requirements as if you ran these full, if you have like 8 times 4, or say like 8 of 4 qubit circuits, as opposed to running 32 qubits, this one runs a lot faster, and it may have similar performance, in the form of loss, accuracy, or even a new utility. Tensor network algorithms, again, a lot of people are going to be running those. They're just not exact like state vectors, and that's an option too, but they're a little bit different. And keep in mind, doing qudits in the future, and dequantizing algorithms with any of these, it may be up in the air too. Okay, so here's the benchmarkings, and this is the Qiskit model. So this is when you open Qiskit, the IDE, and it's within Qiskit Lab. And basically, the model itself doesn't specify a simulator. And that, when I'm talking about that, I'm talking about auto. So I put auto there, meaning that, I didn't change anything with threads. Now, I knew that if you set to the threads equal to 0, uses 1400 right here, it's supposed to be the same as the number of max cores. So Qiskit's saying 8, and then you can see it's pretty similar. There's some fluctuations with this, but basically 0 is the same thing as 8, and everything kind of makes sense here. If I only select a single thread, it's actually the worst, which is expected, and it goes down and down. And what was interesting is 9, because 9 was lower than 0 or 8, which would mean 9 threads and 8 cores, right? And 9 corresponds to 100, which is basically, if you give it too many threads, it goes to the max anyway. And the more of the story is you didn't have to change anything to get the max in here. Now the issue is basically there's issues between PyTorch and Qiskit. It looks like, I don't think it's an issue with the Qiskit CPU, but what this data shows is basically like there's something wrong. And what was interesting is you would expect it all to run better inside of Qiskit, but I went over to Colab, and I don't think, because the Colab devices are better, that these runtimes going up to 2000 seconds or closer to like 87, for the best. Now the other issue here is there's not an advantage in running the best GPU on Colab, which is the A100 or the TPU. Okay, so this curve, is basically this part. The fastest runtime should be the Colab 800, or I'm sorry, the A100. But as far as an efficiency, study with this is basically everything on Qiskit, it's the free tier, right? So I don't think that's the issue with me not having good compute power, and I think it's more the PyTorch issue. Now, on the Colab CPU, it was the fastest. And so the overall cost was, fractions of a penny. And then I calculated the efficiency to about 59, which I did 1 over, it's the product of cost times runtime on that specific one. Now, this next one, these are a lot lower. So you see the highest one doesn't go anything above like 210 seconds. And we'll focus on the Keras one. So you see the Keras one, it's just slower run times. Now, once the stock TensorFlow doesn't work well, so you have to use a previous version. I'll have the GitHub up if you want to see that one. But basically, this is all backwards because the GPUs are supposed to run faster than the CPU. However, because these are in parallel circuits and it's not taking, if I were to run 8-qubit circuits, say for instance, 14 seconds to do, basically these, the model was pretty close to the original one, is not that bad, right? But, again, these are PyTorch and these are Keras compatibility issues. So Keras probably being the worst of the two, but I asked on the discussion forum, if there's going to be a way today, basically to use PennyLane and NumPy, because there's issues here, with, the PyTorch and the Keras. And you can see, so for the PyTorch, it's, faster run times, but in specific, the Cocos.CPU CPU and the Lightning Qubit TPU actually did not run. But the moral of the story is, because of the parallelization of the algorithms, if you look at 14 seconds for default.qubit, which is the most compatible today of the devices, is not too bad. And it didn't even really register on cost with an efficiency of like 2286. But the highest efficiency goes to Qiskit devices because I didn't spend any money, right? So don't take that for granted that these are free devices too. Now, the summary is basically this, is there needs to be better machine learning library compatibility. And, the Qiskit model did not run PyTorch optimally at all, is what it's looking like. And these are known issues. And especially in the PennyLane world too, in their own native IDE. And the top NVIDIA GPUs did not run optimally using, Keras or PyTorch libraries. And then it's basically PennyLane and NumPy. I get the speed ups, so up to 35 times speed faster with the best device, right? Because there's some issue with these machine learning libraries with QML. And, the other thing is quantum algorithms and neural network architectures reveal potential. So an increase in accuracy was observed, adding more of these parallel, quantum circuits in parallel. And an 8x4, for instance, with n qubits was more efficient versus 32 qubits, right? So that was my top algorithm was, with these four layers of rotational Y gates versus 32 qubits. And you could do the math. So 2 to the n, even though you're running many of these in parallel, or you can go up to hundreds or maybe even thousands, is that you're not getting, 2 to the 32 is huge compared to 2 to the 4, right? And runtime is very similar and actually includes M, which is a gate parameter. Now, the smaller parallel circuits, and I saw this in a paper, they said that has a reduced Hilbert space, and that's an issue for researchers, is fully understanding that. So say, for instance, you understood, the Hilbert space of, 2-qubit or, 4-qubit circuit, and then you're just going to run a bunch of those in parallel, as long as the performance there and they're behaving correctly, which they should, because then effectively, if you have that many, so say 32 neurons, classical neurons, instead of one algorithm getting all of it, the same exact algorithms are getting a piece of it. And this is, it might actually be better performance than if you ran the bigger algorithm. So quantum interference, superpositioning, entanglement, what was mostly used in this study was the interference. I didn't set anything into superpositioning and no entanglement. And again, when you're talking about trainable parameters, that's, it's usually an effort to get the one that's better than the embedding. And I've had that happen twice. It's basically, I find my number of layers that works good for, the embedding, or to add on to the embedding. And basically, the potential application is classification and then data set separation. And you've seen these pictures of qubits, with two different parts of the data sets in different parts. So if we can get that, as far as like, if I'm getting 100% accuracy, but my loss isn't still quite zero, it means that the data sets aren't, perfectly separated on the exteriors of the block sphere, meaning that there was some along this path to get a loss that wasn't zero. And obviously less RAM and less time, and these would be benefits. Are there any questions on the slides? I saw a number of people kind of hop on here.
Just gonna say, like, this is super thorough, Kevin. Good job.
Yeah, appreciate it.
Really, really great work.
Yeah, and this is an application, it looks like, and tensor, people just think of circuits just in terms of depth or width. So depth meaning to the right, and then width meaning down, but that's just for a single algorithm. So if you can run them in parallel and then you keep getting better performance, that would be preferred because of the, it's the 2 to the n's, or the 2 to the n's for RAM, and then runtime is actually gates times 2 to the n, where n is equal to qubits. Anybody else? Any particular slide?
So I have a question for QML just in general. Is that okay?
Yeah.
So I did some research also into this. I wanted to know the application for this specifically for like noisy data, due to the quantum nature of this. What are your thoughts on that?
I want to make sure I understand the question correctly. So you had said noisy data.
Yeah, noisy data.
Okay, and we're not talking devices or anything. We're just saying that
Yeah, so like specifically the data when it's noisy, I've seen that it's really good with noisy data. What are your thoughts on using it for that application?
Yeah, I mean, everything is just so specific. So I think that, as we're leaving this phase of basically QML or QiML, the first good models that we had by Pennyling were like 4 years ago. Okay. And I would say that the research is accelerating now with, the BASFs and, NVIDIA doing all these pre-experiments with GPUs and all this type of stuff. And, I don't know if this is considered noisy, but the 200 data set, when I switched from the 2-qubit to a 4-qubit circuit, that helped to overcome, and then I was able to get this separation between that. And I mean, if you had a specific example, but is this for classification, or would this be for so say for instance, do you have an example of the classical task that it's not doing well with the noisy data?
So the information that I got this from was a lecture that I was watching. It was from Ramona Wolf. Have you heard of her?
It sounds familiar, yeah.
Yeah, so I was listening to that lecture. They didn't specify a data set specifically, but they were just pointing out that when you're using QML, specifically when you have a data set that's not like properly clean, and if you keep adding a few more things, you can sort of just how do you say it? You can, as you mentioned here, you can like put it in and make the noise less pronounced in the training.
Yeah, I mean, what comes to mind is like, yeah, like, if you have a bad algorithm and you're trying to, split or parallelize all these, quantum circuits, that won't work. So I'm trying to think what they were saying to you as far as what if it works better with QML in this specific case. But I think what your question is basically like, is QML better with noisy data, correct?
Yeah.
I don't have enough to really answer that.
That's okay.
Yeah. A good question. Anybody else? And I would encourage anybody, like, I mean, this just makes sense, right? Because if the issue with all this stuff with quantum simulators is the RAM and the runtime, you know, just switch to different thoughts. So I was so focused on, you know, depth or width of a circuit, you know, depth being better than the width of it. But like I said, this looks it looks promising because it's basically saying like any of these identical algorithms, they're proven to work good with, say, all of the neurons coming in. So if you just split the task because the issue is, you know, circuits with many qubits and you get that performance boost, then, you know, that would be huge. And I did some literature review with this, and it came to me a little bit later on as far as what was going on based on my results, you know, that, you know, in this specific case, every single time you added, you know, more and more parallel circuits, the loss decreased. And, you know, specifically with this slide for the 400 data set with 4Q layers, going to this 2x64 with the 400 data set, you could see that it's a better data set, right? Because the loss goes down by approximately an order magnitude, so 0.026 to 0.0034. And then you get that accuracy too. And if you look at this data set, it's not as challenging as the smaller one because the way the dots, again, I think it's this one dot that's an issue for most of these 99.5s. So yeah, I mean, it just, I would say a lot of people are stuck on that as far as like, you know, squeezing the qubits out of, you know, whatever. If you can, they said about, you know, 30, you know, for quantum machine learning, which you can still do a lot with, you know, as far as sheer number quantum trainable parameters, and they're cutting circuits to about 100. So getting up to about 100 qubit circuits before cutting and then running it in some fashion. And if you have to, you know, use tensor networks too to get the if you have really high dimensions, right? It's an approximate thing though. So, and with this application, it's basically there's other ways of iterating on it too. Like say, for instance, like these circuits in parallel, they can be different, right? And there's, you know, trying to think what else. You know, stacking. There's different tools, say for instance in Torch, that you can use in concatenation. And this, you know, say for instance that what's presented here is not that you can still develop it further, because if it's like 14 seconds or 15 seconds for the stock, you know, before doing more parallel circuits, then you're effectively just adding more 2 or 4 qubits circuits, which doesn't slow things down tremendously. Anybody else we haven't heard from? So, you know, it seems good, right? And I think a lot of this is like you have to do the experiments, right? So if on paper it's promised to give better, you know, lower losses, higher accuracies, those types of things, after running the actual experiments, does that still hold up? And like this one, you know, I would probably, the first thing is run it with at least a couple other algorithms, different data sets. But again, actually the highest, the best performing algorithm was that it was the 4 qubit times 8 circuit, or yeah, 4 qubits times that many circuits. 4 times 8 circuits is 32. But I had an issue with getting to 4 with some of the PyTorch ones where the code was a little bit easier for me to understand to get to 4 to get that 100% on the harder data set. Yeah,
Yeah, the only thing I was just saying like the only thing that I've been like sort of investigating more of is like doing more of the what would be considered like non-linear functions that are like key to classical machine learning doing better than quantum and quantum machine learning, and seeing how we can maybe do that. So like, sigmoid functions, ReLU, like those kind of things where that's still being done, like all of these packages, they're still like that's being done classically, right? And the only thing that's happening is the featureization and some sort of training that's happening in the quantum circuit. And even that, it's like each iteration as you were going through, right? So that's where I'm trying to see, but like, yeah, it's, most devices can't do non-unitary circuits yet. Or you need to like somehow do some sort of like you said, Q-Quart or Q-Trit or some multi-dimensional quantum circuit to sort of approximate some of these nonlinear setups. So yeah, like that's what I've been seeing. But yeah, any thoughts on like, yeah, have you like looked into anything like that, like seeing, okay, for example, like something like an XGBoost, but like in a quantum algorithmic context?
Yeah, I mean, and this is just from studying all like the PyTorch and the Keras stuff. Is like it seems like it's going to be a while for the fixes to come, right? Because say this got big and what, like 2019, something like that. With Penny Lane, Qiskit really hasn't done much more additions, but you need two. Like you can't just have one QML library. So that's why I keep trying to do the Qiskit stuff too. But like I said, like if you could do Penny Lane and NumPy, and that's pretty much the only thing you do. And they have custom NumPy optimizers. I think that's to themselves. I don't think they're public. But basically, if you can work within that framework to get the speed ups, I got like 35x times faster for A100 GPU versus, say like the slowest setup that I had. And that works. So I would look for those demos in specific, to do research. And I know you can do a lot with NumPy, and because people build circuits in NumPy, but you probably would be doing that in Penny Lane. And that's the one that's working as far as, I think that's the researcher's preference, because at this point, it took me many months to figure out this stuff about PyTorch and Keras, not being optimal. CPU is faster than the fastest GPU. But many times it works, it's compatible. But I think in an industry that's just, based on time, you kind of have to work within that. And I don't know if you could say build up neural networks, using NumPy with Penny Lane's algorithms, because like I said, optimizers and other things are based on NumPy too. But I think you're going to hit all these bottlenecks with PyTorch and Keras in the short term. There might actually have to be standards to make classical ML more compatible with QML. But yeah, your work sounds interesting, for sure.
Yeah, that makes sense. That's a good perspective. Thank you.
Yeah. I mean, I asked him today. I put it in the discussion forum. I said, for classical and quantum algorithms, is there going to be tools available with Penny Lane and NumPy? Because, like I said, the PyTorch, you saw some of the runs actually did not run with Penny Lane. So, anyways, what's going to fuel all this stuff is the industry, like the BASFs and these other huge organizations that use the software libraries, and they say, okay, well, we need this specific thing to work because all of our other notebooks are in PyTorch. And like I said, I don't think that's now, but I think that's coming. Yeah, I think that's high demand.
I have a question.
Yeah, go ahead.
Mentioning PyTorch with Penny Lane. Did you get any good idea, especially with PyTorch, when you have to explicitly state which part actually is some GPU, which part is not? And when Penny Lane is added to it, that actually, I could never get it to work properly. Yeah. Because of that specific, you need to actually explicitly state the location of your computation and data. And with the circuit that needs to be on the GPU and the actual optimization, I actually had tremendous difficulties to specify that.
Yeah,
Do you
I
have-
think the consensus by the researchers is that they say there's issues with PyTorch and GPUs. And again, I'm 99% sure with this is the researchers' preference. If you want to go fast and like far with this, is you're going to be NumPy, PennyLane, some other ones that don't conflict. But default.qubit is the only thing I've got to run on anything with the PyTorch or Torch interface, or saying Keras.
Okay.
TF, yeah.
Okay.
But yeah, I mean, it's possible because, like I said, their first demo is graph embedding, and then I did a bunch, maybe like 15 different devices or 17 or something like that with that demo, and it behaved correctly because it's just NumPy, PennyLane, and then increasing, running in Colab. And so you were asking about that type of stuff. So when you get these compatible notebooks with GPUs, there's a specific. I have it here. When you select, like, say, for instance, in Colab, and I think you could do it locally too, it's this specific code, and there's one for, you should also try Cocos too. So there's lightning.gpu, there's 5 different Cocos you could do, CPU based, TPU based, and then, or at least in Colab, and then 3 other GPUs. So I'll find this and I'll put this in here. Yeah, so and I haven't got as much good feedback from the Cocos, but it's promising, and we haven't quite, or I haven't figured it out. Like it runs correctly, say, for CPU and GPU. This is the one for NVIDIA GPUs, that specific one. And people ask, is Cocos, because when you get over a certain qubit, which wouldn't be for parallelized algorithms like this, once you get over a certain amount, that yeah, anyways, the bigger devices tend to work better at higher qubit counts. But obviously this demo was like 2 or 4 qubit with a bunch, right? So a bunch of those. But the other one for Cocos is, they say the CUDA, the 11 works better than 12, I think, by and large. That's the one for Cocos. So, and there's optimization very likely coming with this. NVIDIA it basically started a lot of this stuff. They were running 4,000 GPUs and getting, over 1,100 qubit circuits simulated in some of these, right? So very high qubits. So just to see if this stuff would make sense. And it's all hinging on capitalizing from that quantum physics, from quantum interference or superpositioning or entanglement too. And in the future, you might have a mix of these things. So bigger linear state vector algorithms, tensor algorithms, state vector algorithms, parallelized, smaller ones. But there's the optimization, I don't think, is fully hit. So say, for instance, like the CUDA could recognize, say, like thousands of small parallelized, quantum algorithms. It's usually the default.qubit that it's stuck, especially for PyTorch or Keras. But the tools are out there. Everything NN dots and sequential. You can still do all that stuff. Anything else? Anybody that we haven't heard from yet? And that's my advice, is just run experiments. That's the only way, right? And then you'll get better at finding out what the better experiments are. And I wasn't planning on talking anything with parallelized quantum circuits. And after I started doing this, I was like, what if I made this? The code's huge, but it runs relatively fast because they're just small 2-qubit circuits.
Yes, I have a comment. I agree completely with you about running multiple experiments, finding the best method. But also I find valuable to run multiple instances of the model itself, so that especially when the initialization of your parameter space is random, and you may have completely different results each time you run it. So I think it's very important to run multiple instances of the model, and then actually be honest when it comes to the distribution of your results. Because I have some tremendous variance between your best and the worst results. It could be very large.
Yeah, I mean, that's always the goal, is to keep all your data, when you run. And I mean, for accuracy or loss, all the runs are the same, the first run or whatever. But for run times, you mentioned initialization, is if I'm doing a good study, I'll just rerun it, because always the first run fluctuates more across everything. So they're really actually the second runs. But say, for instance, if you want to do a sequence and you run for the first time, that one is going to be relatively slower than the second and third. But whereas the second throughout all that, subsequent runs, if you're doing like, pentakits or whatever, five of them, those will be closer if you throw out the first one. And then, can you set a random seed, to make sure the parameters are set, or?
Well, in my case, I was studying barren plateaus, and so the impact of initialization could be tremendous. So if you fix your seed, you always get the same result, but that may not be actually the optimum, because there could be very large variance.
Yeah, those are good experiments too. Are you familiar with these Los Alamos National Lab papers, the challenges and opportunities of QML? And then there's a trainability issues one too. And I wanted to include some of the material, but I'm not quite sure, because say, for instance, there's noise-induced barren plateaus, which should be specific for hardware. And there's other ones they, just say like, more qubits or entanglement. I wasn't quite sure if that's just for hardware or if that's for other, for pure simulators.
I have a paper coming just in quantum information processing, where we actually look at 4 different methods of dealing with barren plateaus. And there is about 6 different aspects that can cause barren plateaus in a process. And each time you take one of the mitigation strategies, it actually influences trainability. So you want to deal with barren plateaus in the absence of barren plateaus, and you make it worse. So that's why experimentation is so important, that you don't try to blindly apply one of the barren plateau strategies unless it's needed.
I'll see if I can find these. Like the first one, I think for anybody would be the challenges and opportunities with QML. And they do talk about tensor networks, so this is classical data generating and classical data processing. They do talk about, I just, some at some points of these papers, I don't know if they're talking about also for simulators, right? Because I don't know. Say, for instance, like for barren plateaus, if you go, many more qubits, is that the same thing on simulators, right? Because they'll be talking about hardware and QiML at the same time.
And definitely noise itself could cause barren plateaus.
Yeah.
Or it makes it indistinguishable from the actual error space versus noise.
Yeah. And you know, because in some of these results I got, the loss kept going down, but say in the earlier, you know, so say if I went from like, you know, a certain number of layers, you know, doubled it or tripled it, and actually the accuracy went down. So that's probably evidence of this egg crate, you know, lost landscape that's out there, right? And you know, it's the same issues, right, that machine learning has.
Yeah.
But yeah, these papers in specific are helpful. It's just, you know, sometimes because there's a lot going on, I'm not quite sure exactly what they mean. And they've kind of led, in my opinion, you know, this whole work towards, you know, machine learning. And obviously we have it now. Anybody else we haven't heard from? Then Samarth or Walter? Or Caval or Alan? And I'm looking up the QML papers. Just a hint, because this was in, one of these was in Nature, but if you actually, the other one was trainability issues. Here's one of them, but you should, this is actually in Nature and it's openly accessible. And it just helps to connect these, you know, concepts between qubits and, you know, layers and that type of stuff. Now the other one, trainability issues, is newer. And I guess for developers, subtleties in the trainability of QML models. For developers, this one's a little bit more, you know, hands-on. So that second one. And obviously, you know, there's a lot of good papers out there.
Mm-hmm.
And, you know, the other stuff is basically if you're really good, you know, with the book work, with the papers and stuff like that, I would highly suggest being an expert in Penny Lane or Qiskit, you know, with the machine learning work, because ultimately that's what you're going to be working on, right? It's not going to be, you know, this awesome thing 5 years down the road or anything like that. It's, you know, these are the tangible things.
Yeah, so I have just one more question.
Yeah, go ahead.
So what problems do you specifically see QML solving, or what problems do you see like quantum machine learning specifically tackling as you have seen it today?
Yeah, you know, it's definitely because we're taking all this, it's not efficient to simulate quantum bits, and we're taking all this time, especially for bigger circuits and RAM to do all this stuff. So for instance, it's kind of like I look at it like when you first start studying quantum algorithms, like what is that quantum algorithm benefit over that any classical algorithm, but now we're using it with GPUs. So GPUs with quantum algorithms. And you know, there's a fair number of papers, you know, Seth Lloyd, Maria Schold, Kristen Temme, that they've worked on embedding work, and they call it quantum metric learning. And you could go straight towards training the embedding if you want to. And anyways, I've watched presentations. I think it was Maria said at some point, you know, for classification or like data set, you know, separation, that the embedding is the most important part. And sometimes you don't actually need a variational layer. So, you know, say for instance, like, you know, we have these, you know, simulated qubits, and then how can we have data sets fit on polar opposites, right? So this would be a loss of 0, right? And, you know, you saw some of these getting down to 0.00 something. So it's getting more towards that. But I think in the near term, I think we'll figure out things in classification. It's such a, you know, broad subject. And if we have to, you know, go to QDITs. So say, for instance, like I could do multiple 10-dimensional QDIT parallelization of algorithms, and they're all a single wire. So meaning that yes, it takes more effort for a 10-dimensional than a qubit or two. You know, but stuff like that, like it'll be like this specific application with this, you know, number of qubits running in parallel, or, you know, tensor networks, or, you know, straight state vector, but something more for like data set mapping. In theory, you know, you could still get a fast runtime on a simulated quantum algorithm, because the algorithm itself is a quantum speed up. So we'll see how much we can keep as far as faster speeds. But I think, you know, on the performance side, lower losses, higher accuracies, and then also utility is huge. And I think that actually, you know, maybe right up there with performance, you know, how, you know, in specific, can quantum interference and, you know, superpositioning entanglement, how is this very unique thing that can't ever be done classically, you know? So there's classical algorithms, all of them can be simulated by quantum algorithms, but not all quantum algorithms can be simulated, you know, using traditional classical algorithms. So yeah, those two things, you know, utility, better performance. These results are very encouraging. Sometimes you just have loss go down. I mean, you have to run many different times to kind of like back up what you're doing. And some people don't want to put in the work to basically make this specific, you know, quantum parallelization bigger. But, you know, you have to run a lot of experiments. Yeah, so there was a question. Yeah, the slide should be up either tonight or tomorrow. I'll have the GitHub up too. It's just a file name, you know, they get kind of long issue. And any other questions or comments? Yeah, anybody that we heard from before, or anybody new? Then if not, let's see where we're at here. Yeah, so this has been discussion 112, Thursday, December 7th, 2023 for advanced PyTorch and Keras deep learning with QML/QiML. Thanks everybody for coming on, and have a good rest of the night, and have a productive rest of the week. Take care, everybody. Bye.